discuss about what is meant by energy and which are the types of energy. That is mainly we will discuss about kinetic energy and potential energy. Okay. Energy, it is defined as the ability to do work or capacity to do work. Capacity or ability to do work. That is known as energy. That is, if a person is having energy, he has the ability to do work. Or we can, in other words, we can say any object, whichever is doing work, we can say it is having energy. Okay. So that is what is meant by energy. So energy has the same unit as that of work. The SI unit of energy is 2. Various other units are there. Kilowatt hour is one of the unit of energy. Commercial unit of energy. Another CGS unit of energy is F. But the SI unit is, SI unit is 2. And you know the relation between all those units. Okay. Now we will discuss what is meant by kinetic energy. Kinetic energy. Kinetic means something related to motion. So we can say that energy possessed by an object by virtue of its motion is known as kinetic energy. So can we define energy possessed by an object by virtue of its motion. The energy possessed by an object by virtue of its motion is known as kinetic energy. Or energy possessed, energy of an object due to its motion is known as kinetic energy. So if a moving object, moving stone or moving ball, if it stops or if it collides with a stationary object, what happens to that stationary object? If its mass is less, we can say that that object will move. It means that moving object can move. Okay. Similarly, in a moving bullet, when it pierces a wooden block, that it moves through the wooden block. In that case also we can say that it can do. So any moving object can do work, or in other words we can say that energy associated with moving object is known as kinetic energy. Now we are going to find an expression for the kinetic energy. For that we are considering an object. Mass of the object, let it be m. M is the mass of the object. And it is moving with a velocity, initial velocity. U is the initial velocity. Initial velocity of the object, let it be. And a force is acted on the object. Because of the force, its velocity changed from u to, okay. So F is the force acting on the object. And because of the force, its velocity changed to v, that is the final velocity. And during that change in velocity, let the displacement be s. S is the displacement of the object and A is acceleration. Because a force is acted, because of this there is an acceleration. So we can find an expression for work done. So work done is equal to F dot S, scalar product of force and displacement. Since force and displacement are in the same direction, we have to write Fs cos theta, or we can write F into S, because theta is equal to 0 degree. It is in the same direction as that of displacement is in the same direction as that of force. Now we can substitute for F. By Newton's second law of motion, here mass remains constant. We can write F is equal to ma into S. And instead of S from the equation, we can write V square equal to U square plus 2ES. Or instead of AS itself, we can write V square minus U square by 2. So that we can substitute here. So m into V square minus U square by 2. Or we can write this work done will be stored as the kinetic energy. So we can write kinetic energy is equal to half m into V square minus U. So the kinetic energy, if the object's velocity varies from u to v, kinetic energy is given by half m v square minus u square. And if the object is moving with same velocity, initially it is 0, in that case we can write kinetic energy is equal to half m v square if it is starting from rest. Or if it is nothing specified, the object is moving with a velocity like that, and it is given, you can take kinetic energy as half m. Okay. So the expression for kinetic energy is given by half m v square, and the same expression we can represent in terms of momentum that we will discuss. So kinetic energy is equal to half m v square. We are multiplying both numerator and denominator of RHS by m. So what you will get, kinetic energy is equal to half m v square into m divided by m. It will not make any difference. We are multiplying it by what, like that. No? What you will get, kinetic energy is equal to half m square v square by m, or we can write 1 by 2m into mv the whole square, or we can write kinetic energy is equal to v square by 2. So this is the expression for the kinetic energy in terms of momentum. Kinetic energy is equal to v square by 2. So sometimes in problems they may give two objects of different masses are moving with same momentum or having same momentum. Calculate the ratio of their kinetic energy. Or sometimes they will give two objects are having varying kinetic energy ratio is given. Calculate the mass ratio. If the momentum are equal, like that, it will be given. So you can solve those type of problems. By using this formula also, kinetic energy is equal to half mv square also you can solve, but only one thing is that there it will be a bit complicated. It takes more time, but here if you use this formula directly, it will be easy to solve it. Okay. Or we can represent momentum in terms of kinetic energy. It is given by root of 2m into k, where k is the kinetic energy. Okay, is it clear? Understood? So in this we have discussed already about kinetic energy, and now we will discuss about work energy. Work energy. So from that term itself, it is clear that this theorem relates work and energy. Which energy? Kinetic energy. So So first of all, we will write the statement of work energy theorem. Later on, we can discuss it. The work done by a force is equal to the change produced in the kinetic energy. The work done by a force on an object is equal to the change produced in the kinetic energy of that object. Okay, so we have to show that work done is equal to change in kinetic energy. So we are starting from the third equation of motion. Third equation of motion is given by v square equal to u square plus 2as. That is object's velocity, initial velocity is u, a is the acceleration, s is displacement, and v is the final velocity. So we can write v square minus u square equal to 2as. So here all those data we have to write. What is u? U is the initial velocity, v is the final velocity, a is the acceleration, and s the displacement, and m is the mass of the object. So whenever you are writing any equation or deriving any equation, first of all you have to mention which are the letters or what is meant by those letters that you are using that expression, you are using in that expression, that you have to specify. This is very important. Okay. So v square minus u square equal to 2as. So multiplying this equation by half, equation 1 into half. We are multiplying entire equation by half. So what you will get? Half m v square minus half m v square equal to half m into a into s. Half m into 2as. So this 2 can be cancelled. So what you will get? Half mv square. This is final kinetic energy. So kinetic energy final minus kinetic energy initial equal to m into a into s, and that is m into a is the force and s is the displacement. So what we can write? This is equal to so we can write kinetic energy initial final minus kinetic energy initial is equal to that of the work done by the force is equal to change produced in the kinetic energy of the object. Okay, so this case corresponds to constant force. So this is the situation where constant force is active. When constant force is active, we can show kinetic energy. Change in kinetic energy is equal to 0. Okay, and next we are going to discuss about same work energy theorem for a variable force. Work energy theorem for a variable force. In the previous case we discussed for a constant force, and here we are going to discuss about variable force. Statement is same as that of previous one. It is work done by the force, variable force. Total work done by the variable force is equal to the change produced in the kinetic energy of the object. Okay. So we are considering an object, and let F is the variable force acting on the object. Variable force vector, and let displacement vector and let dw is the small amount of vector. dw is the small amount of vector. So the small amount of vector dw we can write it as dw is equal to f dot s. If the displacement of the object is in the same direction as that of force, we can write theta is equal to 0 degree. So in that case, dw is equal to f into ds. Cos 0 is okay. And again, dw can actually f can be written as mass into acceleration, ma into ds, and acceleration can be written as rate of change of velocity. So dw is equal to m into dv by dt into ds, or we can write dw is equal to m dv into ds by. And what is ds by dt? Rate of change of displacement, that is equal to velocity. So what we will get? M v dv. dv is there. Instead of ds by dt, we can write velocity. So what we got? M v. Okay. So we got dw is equal to m v. Now integrating both sides. Integrating so here which is the variable? dw is the variable. So for w is the variable, work done is the variable. So that work done varies from 0 to w. Total work done dw is equal to here which is the variable? The variable m or v. Mass is constant, variable is v. So the velocity changes from u to v. We can write m can be taken outside the integral. 0 to v, sorry, 0 not u to v. Initial velocity is u to v, v. Why we are writing u to v? Because velocity is the variable. Its value initially is u and finally it is v. If you integrate here, what you will get? You will get w between the limit 0 to w, and here you will get v square by 2 between the limits u to v. So you are getting, you can write here integral x raised to n dx is equal to x raised to n plus 1 by n plus 1 plus the constant of integration will be there, and here we are applying the limits, that constant of integration. Okay. Now you can give upper limit minus lower limit, but you will get w minus 0 is equal to n by 2 into v square minus u square, or you can write w is equal to half m v square minus half m v square, and that is again is equal to work done is equal to change in kinetic energy. Work done is equal to final kinetic energy minus initial kinetic energy. The total work done is equal to change in kinetic energy. This is for variable force. So whichever is asked, accordingly you have to write. If they are asked to write work done by constant force, that you have to write. Otherwise, if they are asked to write work done by variable force, this you have to write. If it is not specified, either of them you have to get. Okay, clear? Potential energy. Potential energy is defined as the energy possessed by an object due to its position in the gravitational field. Not only gravitational field, maybe electrostatic field also. So due to its position in the field of force or due to configuration. Okay. Potential energy is defined as the energy possessed by an object due to its position in the field of force or due to its configuration. So the energy possessed either due to its position in the gravitation, not only due to its position in the field of force, or due to its configuration. So example, this an object which is kept at some height is having energy. That energy we can say as potential energy. That energy we will say due to its position in the gravitational field. So we will say gravitational potential energy. Similarly, if different charges are there in space, so because of the charges, because of the force acting on one charge due to another, if another charge is kept, it will be experienced by force, because of which we can say that since it is in the position of the field of another object, it has energy, and that energy we say that electrostatic potential energy. Similarly, water stored in a tank is having energy. Water stored in dam is having potential energy. That is the energy due to position in the gravitational field. Similarly, this stretched bow, and if you are throwing arrow from the stretched bow, it is moving because of that stretched bow has energy due to strain or due to configuration. Similarly, catapult. You can throw a stone from a catapult because when you are stretching that catapult, it has energy due to configuration or due to that stretching, it has energy. Similarly, like that, so many examples are there. A stretched spring. A stretched spring is there. So if you compress and if you release it, but you can see if an object is kept here, it can move the object because this stretched spring is having energy. Okay. So these are the various examples of potential energy. So based on these examples, we can classify this potential energy into three categories. One is gravitational potential energy. Gravitational potential energy. Then instead of potential energy, I am writing PT. So we can write gravitational potential energy. Next one is electrostatic potential energy. So from those words itself, it is clear. Gravitational potential energy means energy possessed by an object due to its position in the gravitational field. Here, energy possessed by a charged object due to its position in the electrostatic field. And last one, elastic potential. These are stretched rubber band, catapult, stretched bow. All those are examples are elastic potential. So now here we will discuss about gravitational potential energy and elastic potential energy. And this one you will study next in 12 you will study. So first of all, here we will see gravitational potential energy. An object is in the ground level. An object of mass m is in the ground level. that object to be taken to a height h. So when we have to take that object to a height h, we have to apply without any acceleration that object to be taken from ground to. Okay. So what we have to do? We are not applying any acceleration, but the acceleration due to gravity will be there. So we have to overcome that force of weight. So we have to apply a force. Here, what is the force acting? Mg is acting vertically downward. So we have to apply a force which is exactly equal to mg. Then only that object can be taken to that height without any acceleration. Okay, is it clear? So mg, minimum force needed, is equal to mg. Now we can write the expression for work done. Work done is equal to F dot S. So we are applying force mg in this direction and object is getting displaced in the same direction. So here we can write F S force 0 or F into S, or work done is equal to, what is force? Force is mg and displacement is h. So work done is equal to mgh, and this work done is stored as the potential energy. Gravitational potential energy is equal to mgh. Gravitational potential energy of the object taken to a height h is given by mgh. So here one thing you can notice is that through whichever path it is taken, the gravitational potential energy remains same. Whether you are taking through this path or whether you are taking like this, or whether you are to this path, or whether you are taking like this path. So whichever path, this is A, this is B, C. So whichever path, whether you are opting A, B or C, it is immaterial because the work done depends only on the displacement. What is the final position? What is the initial position? Through which path it is taken doesn't matter. So gravitational potential energy remains same provided the same object is taken to the same height by different paths. Okay. So gravitational potential energy is given by mgh, and in problems when you are solving you have to substitute g as 9.8. If it is given in the problem as 10 meter per second square, you can take it as 10 meter per second square. Otherwise, you have to take it as 9. Okay, is it clear? So today we discussed about what is meant by energy, which are the two types of energy. One is kinetic energy and another one is potential energy. I hope all of you understand.